Come on, go there. Okay, I decided on the fly, instead of starting with this, to start by just looking at the worksheet. Wow. I'm not taking record today simply because if you're absent, it's excused, and I figured why have to deal with that on the record sheet. So notice that I did post as promised worksheets. The worksheets were promised Sunday. The YouTube videos showing solutions, the first two were completed by Monday, but it wasn't until I think Wednesday that I completed the last one, and I put a message to you about it. And then two students contacted me yesterday saying, can't see the solution for the last one, so I found where the problem was and got that fixed. So now you can see all the solutions on YouTube for the problems, not the conceptual questions. I'm not going to go through answering these conceptual questions here, but I did want to point out on the problems here, you have all the work here so you can see how the work is done, but it's probably more instructional if you listen along on YouTube if you don't understand. If you understand, why waste your time? But if you don't understand, then you can listen on YouTube and see why I did these things. I tried to make this following the idea of the worksheet as, fill in the blank as possible for the ideas along the way in organization. Nothing special to say about this one here, but for chapter 14, there is something special to say. I had those same two students who told me that they couldn't view chapter 15 also point out that they got different calculations for these three right here. If you look at the worksheet, I have carefully changed one number that I had written wrong when I did it on YouTube. That is, I forgot the starting temperature and I put 273.15 when I was writing it here. When I did my calculations, which I did beforehand, I put in the correct starting temperature of 293.15. So after students point out the numbers don't match, I came back and fixed those 7s to 9s in I, Roman, in part I, Roman numeral 1, and part I, Roman numeral 2. So if you go through and like you're watching the video on YouTube, when you get to this, I will probably say 273.15 and I will write 273.15. And then I'll say that equals and write down the values here. The values are correct that I wrote down except for that temperature because I did the calculation separately. Just want to make sure people are clear on that little mistake I made. So this one here had 3 problems. The last one here, oh wait, no, that's not the one. Maybe it's the first one. Yes, the first one is the calorimeter problem. We learned everything to do these in class, but we didn't do an example of one. I didn't do one in class, nor did I give you a homework problem, I don't think, with the calorimetry problem. But the only thing you need to know that we didn't do in class is that when you have a calorimeter, it's completely insulated. So if they say you have a completely insulated system or you have a calorimeter, either one to you means that the heat is 0. So in this problem, I put that no heat can be exchanged in the description so that you have everything you need to do it. So in that case, you start with this equation, total heat is 0. And so you just have to calculate the heats for each of the items, add them up, and set them equal to 0. And the thing you don't know in this case was the final temperature. And that's usually the case. Sometimes they'll say you have water and aluminum starting at this temperature with these masses. You put an object in with this mass at this temperature. It ends at this final temperature. What's the specific heat? Right? They can ask you for different variables, but usually they ask you for the final temperature because that's usually the one you don't know. You can measure all the other things when you start and want to know what's the final case going to be. So I gave you one of these so you'd have practice for a specific application of the principles that you've learned that we didn't do in class. And you'll notice this is in chapter 14, but I asked you about the entropy. Because our test is going through chapter 15, I figured let's throw that in so you can get the practice with it, instead of just waiting to 15 and then making up a new problem for doing the entropy calculations. And you'll notice on this one, I calculated over here. This is the way. Oh, that's great. This is the way the textbook does. I seriously tried to change the pen there. This is the way the textbook does it. It uses the equation that change in entropy is equal to heat over temperature average. That equation is correct if you have a constant temperature. If the temperature is changing, it's not correct. But as you can see from the result here, those numbers 2.05 minus 1.886 compared to the correct values, they are the same. So I will give you on the test the correct equations for the change in entropy and the work for different systems that would require calculus to actually get those equations. Now, the people in Physics 251, you might be asked to find those equations. You'll know the answer, but you'll have to find it, show the calculus to get there. But I want to make sure we have some understanding of these things. I looked up these numbers to make sure they're reasonable. In a dry sauna, a typical temperature in the dry sauna is like 175 Fahrenheit, which is really significantly warm. And we're just talking about the radiation heating here. Sure, you are going to have probably a little bit of conduction from the seats, but not very much. And there could be some convective heating, but since it's dry, it's going to be minimized. If it was a wet sauna, you'd have a lot more. So that's why it's using the power for the radiation. And remember, power, what's the definition of power?
Work over time.
Okay, work over time. Or making it more generally, energy change per time. Because work is one form of energy change, heat is another form of energy change, right? It's transporting energy. And so these equations in the textbook, it writes them as Q over delta T equals. Wow, this pen is too fat. I don't know why, but I had to reset up my pens this morning, and apparently I chose too fat a pen. Okay. So Q over delta T is what the temperature or the textbook puts in, but that is still a power. And so that's why I use the term power. Yeah, the last thing to consider here is, yes, there is a number there. I was like, that doesn't look like it's the same problem. This problem here, the picture helps you to understand you have a hot reservoir, a cold reservoir, and two cylinders going between them. And you're asked questions like, what's the temperature where the two cylinders meet and how fast does heat flow? What's the power? And it's more complicated because, well, you only know the starting and ending temperatures and you don't know the middle, right? It's a little more complicated. Well, what you have to do is say the rate that heat is flowing out of the hot reservoir is going to be the same as the rate that heat is flowing into the cold reservoir. And so I can use the equations for the rate that heat flows through here and the rate that heat flows through here. That one also is too fat. And if you set those equal to each other, then you can solve for the temperature in between them. And once you know that, you can solve for the rate that heat is being transferred between the two. So this one here was using the conduction equation because heat going through a rod is conduction. And so that's where you have the equation there. Just wanted to make sure I go over these problems real briefly so you have a better idea if and when you look at them. These worksheets should be very solid review for the test. Not saying these are the problems on the test. Don't get me wrong, because sometimes people want that. It wasn't the same problems. But if you can do the principles in these, you should be well set up for over half of the questions on the test. Emily.
So you're saying that if we know the stuff on the worksheet, we don't need to study other materials. It would be sufficient enough to do well on the test.
I said over half of the problems. Right? Not all of the problems. So you do want to look at other things as well, but this is going to be the most beneficial single thing to go over. Yeah.
But you still want us to review the textbook and stuff so we can know about the the knowledge one?
Yeah, I have knowledge questions here as well. But yes, you should still do the normal things you would do in addition to this, but make this a higher priority because this one here is more focused. But you're still going to have stuff that's not in the worksheet. Right? That's the thing, like what Emily was asking. I want to make sure it's clear. Don't just study this and forget the rest.
So
Michael.
we have to look over the worksheet and the textbook to kind of get
Yes. Yeah. So like I said, if you can do the stuff in the worksheets, which is much more concise, I think, than looking through the whole textbook, that'll give you more than half of what's on the test. But it's not going to give you everything that's on the test, right? You can't just do that. I mean, unless you're satisfied. Well, I'll get over 50% on the test. Well, I guess then. Any other questions before I go to my review proper? Oh, wait, I should go to chapter 15 before I go to the review proper. Chapter 15 only had one problem, but in the words of Needle-Nosed Ned, it's a doozy. For those of you who like Groundhog Day. Ned Meyer, Needle-Nosed Ned. So this problem here is a heat cycle. It's a cycle that starts at A and comes back to A. Remember when we talked about heat engines, we said the change in internal energy has to be 0 for a cycle in a heat engine, otherwise it would burn up or freeze. Well, it's actually more general than that. Anytime you come back to the same pressure and temperature and number of moles, of course you're going to have the same volume if it's an ideal gas, P equals nRT, and you're going to be in the same state. It's for that reason that we call pressure, volume, temperature, and number of moles the variables of state. If you know those values, you know the state exactly. You know everything there is to know about the system, which means that you have the same energy, the same entropy, the same enthalpy, the same Gibbs free energy. They're all going to be the same things. Those are state values. So if you do this whole cycle, what should the total change in internal energy be? If you start at A and end at A, what should the change in internal energy be?
0.
0. What should the change in entropy be? Zero. That's right. Because it is a variable, or not a variable, but a state value. It's not a variable of state, it's a state value. And if we had gone through enthalpy, Gibbs free energy, you talk about those in chemistry a fair amount. We don't talk about them that much in the introductory, well, we don't talk about them all in an introductory physics class. Those should be the same if you're back at the same place. So the first thing you had to do is define what the types of state transitions were. I probably should have put an adiabatic transition here as well. I should have had like an adiabatic expansion, isothermal expansion, and then, isobaric and isochoric. That way you would have had practice with all 4 of the fundamental transitions, but I didn't. Notice I do have a typo here. Calculate the temperature, volume, and temperature. That would be a little redundant to calculate temperature twice. Temperature, volume, and pressure is what it should have said. There is another place where I said I was going to change the word, and I don't remember where it was. Anyway, so I went through here, and I calculated the variables of state. Where is my table? The variables of state for each of the 4 states, and then I calculated the transition values for each of the transitions. And it's important that you realize there are more than one way to do some of these calculations. So I chose one method of calculating things, but you could have calculated, the heat calculation. You could have calculated using the work calculation and the internal energy calculation and the first law, or you could have gone directly to a heat equation. There's more than one way to do it. No one, at least in my world, is going to mark you wrong if you do it a different way than I do, as long as it's a correct way. So I put down a sequence of steps to do it correctly, but there are other sequences that you could come up with. But this gives you plenty of practice on how to do the calculations for the transitions and how to calculate the variables using the ideal gas law. Now I'm ready to go to my review proper unless there's questions. All right. So reviewing for exam 4, which is over chapters 13 through 15. Just thermodynamics. By the way, I did put a homework assignment up this morning that covers chapter 16, just sections 1 and 2. That's not due until Wednesday. I know I could have put it during the week, but I want people to actually focus on preparing for the exam and not, well, I better do this homework after the exam. Then you can have time to devote to the homework. So chapter 13, these are all the topics that were covered in chapter 13. We had the Zeroth Law of Thermodynamics. That was there in the definition of temperature. Now, it's best to just review all 4 laws of thermodynamics at once rather than saying, okay, here's the zeroth, and let's later talk about the first, second, third. So the zeroth law, very basic. No one would get confused about it because it's so basic, and that's why it's the zeroth law. If object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. More important to that is what those words mean. What does thermal equilibrium mean?
Same temperature.
Fundamental answer, same temperature. Thermal equilibrium means if you take 2 objects and you bring them into thermal contact, so heat can flow between them, that heat won't flow. And that, according to the second law of thermodynamics, occurs only if they're the same temperature. So the answer that Dimitri gave is a perfect answer. Thermal equilibrium means same temperature. I'm giving you the reasoning why so that it can help make more sense. First law of thermodynamics. Simple statement, what is it? Energy can be created or destroyed. And so we usually write that out as a mathematical equation that says the change in internal energy is equal to the heat added minus the work done by the system. Or in other words, the change in energy is equal to what you put in one method minus what you take out in the other. It makes perfect sense. Remember, you can have heat taken away. That's just a minus heat added. You can have work done on a system. That's just negative work done by the system. Third law. Oh, wait, second law. Second law comes before third. That's the way numbers go. Second law has lots of statements. The first statement we learned was that heat naturally flows from a hotter object to a colder object. I think that's the Clausius statement. There's names for all these different statements. Another one is that the entropy, any process has as an outcome the entropy of the universe increasing, or as a minimum staying constant. Another statement is it's impossible, this is actually a statement of the second law, it's impossible to make a heat engine that has 100% efficiency. That's another statement of the second law. So it has lots of outcomes. By the way, something I didn't talk about is perpetual motion machines. What is the idea of a perpetual motion machine? It never stops. Perpetual motion. That means that you have no energy loss. Because if it loses energy, it's going to eventually stop. But the second law says in that statement that you can't have a perfectly efficient machine. You're always going to have energy loss. And I actually had a colleague whose wife simply didn't believe this. Right? She wasn't a physicist, and she thought, that's bunk. My husband does not know what he's talking about. And so she would go on business trips, and she would go to little gift shops and buy perpetual motion machines they sell in gift shops. You guys ever seen perpetual motion machines in gift shops? Okay, a few of you have. She would buy them and bring them home and say, see, they exist. And then he would have to take it apart, destroying her toy, and show her, see these batteries? That's why it keeps operating. It's really pretty obvious that these things are fake when you can start it like thing that goes like this, and you can start halfway down, and pretty soon it's going all the way to the top. You know that something gave it energy. Now that brings up another thing that some people believe, that you should be able to make a perpetual motion machine that you then use to generate energy. What would that be a violation of? The first law, the conservation of energy. That's why Homer Simpson so famously said, when Lisa creates her perpetual motion machine, Lisa, in this house, we obey the second law of thermodynamics, or first law of thermodynamics. Wow, I said that wrong. And it's great because, what does Homer know about physics? He just works in a nuclear power plant. Okay, moving on. Third law of thermodynamics. Very, very simple statement that we really don't need to worry about except for we need to know it. Nothing can reach absolute zero. That's the third law. So those are the four laws, 0, 1, 2, 3, of thermodynamics. Make sure you can clean and make sure you know when to use Celsius, when to use Kelvin. When must you use Celsius?
If the answer is asking for Celsius.
Okay, you just gotta go. If the answer is asking for Celsius, there are a few cases that we haven't seen where we'll give you equations that ask you to use Celsius. But in thermodynamics, you never have to use Celsius unless it asks you. Give me the answer in Celsius. When do you have to use kelvins?
When it's not a ratio.
You have, not when it's not a ratio. You have to use kelvins anytime it's not a change. If you have something that's based on a change in temperature, since Celsius and Kelvin changes are the same, you can use either one. If it's not based on a change, you have to use kelvins. If it is not based on change, if it's not delta T, then you must use kelvins. If it's delta T, you can use Celsius or Kelvin interchangeably. No, because a change in 1 Kelvin is the same as a change in 1 Celsius. That's why you can use them if it's a change. Michael?
They're interchangeable. They're the same scale.
For a change.
Yeah.
Yes, for a change, but only for a change. If it's something like, for the kinetic theory of gases, 3/2 NKT, that's got to be kelvins. And even if it's a ratio, I think that's what you said. If it's a ratio, just imagine if you're taking the ratio and you have one starts at a temperature of 0 Celsius. Well, that's going to mess up your results. It's got to be kelvins in that case as well, even though they cancel. Okay, thermal expansion. Things expand when they heat up because higher temperature means the molecules are moving faster. Moving faster, they bounce off each other harder and they space out more. And we linearize that to say that the change in length is equal to the original length times some coefficient, and that depends on the material, multiplied by the change in temperature. What units should you use for the change in temperature here? Celsius or Kelvin. That's about the only place. Volumetric expansion, same equation except for change L's to V's and change alpha to beta. And in general, beta is 3 alpha. So if you're given alpha and it's a volume expansion, just use beta equals 3 alpha and go on. It's not always true, isotropic, whatever. Iso something or other. Things that don't expand the same in all directions is what the word means. Then beta is not going to be 3 alpha, but we're not dealing with that. So volumetric expansion, you have to use that if you're working with a liquid, because liquids are same in all directions. If you're using a solid, depending on the solid, it may not be that way. Molar and atomic mass, we now know what a mole is. You probably all knew beforehand, but a mole is just 6.022 times 10 to the 23rd molecules. And so the molar mass is the mass for a mole of molecules. And we define the mole based on the gram, so that 1 mole of hydrogen has a mass equal to the atomic mass units in grams. Ideal gas, you should know what the definition is for ideal gas. Something that has no volume and doesn't interact unless they collide, in which case it has perfectly elastic collisions. And when is anything ideal? Truly never. But approximation, if it's high temperature, then the kinetic energy the molecules have is going to be large compared to any loss they suffer when they collide. And so it's approximately elastic collisions, and thus we can go approximately that. The other one is no volume. If the molecules are very rare, that means low density, then the space between the molecules is very large compared to the size of the molecules, and you can approximate the molecules to having those size. So ideal gas laws only work if you're at a temperature well above the boiling temperature and if you have a low density. We had these laws: Charles' law, Boyle's law, Gay-Lussac's law, and Avogadro's law. You need to know none of those. Why do we go over them? Because those are what bring us to the ideal gas law. The ideal gas law is just combining the information from those four laws into one equation.
We just need to know, like,
Go ahead. Need to know what?
like, what they stand for, or like.
All you need to know is the ideal gas law. That's why I put it in red. All the other ones you can get from the ideal gas law. If you hold temperature and N constant in the ideal gas law, then you will get PV equals PV, which is what you have with Boyle's law and so on. So you don't need to know those other laws. They're historically important, but once you get to the ideal gas law, they no longer are important to go back to. Kinetic theory of gases, that's the big derivation we did to determine that the temperature is proportional to the average kinetic energy of a gas. So you don't have to do that derivation, but you should know that outcome. That the kinetic theory of gases is the derivation to show that the average kinetic energy is proportional to temperature. And of course, that equation was kinetic energy average is equal to 3/2 kT for a monatomic ideal gas. And then we came to the Equipartition Theorem that said that you actually have 1/2 kT is equal to average energy in each degree of freedom. And so remember, we talked about if it's a monatomic ideal, it has 3 degrees of freedom. Momentum in the x direction, momentum in the y direction, momentum in the z direction. If we have a diatomic ideal gas, at low temperature, it doesn't have enough energy for anything but those same 3 degrees of freedom. At higher temperature, you get a high enough temperature that you can start having, I think it was rotations first. And so at room temperature, diatomic ideal gas has 5 degrees of freedom per molecule. And so the average kinetic energy is 5/2 kT. And if you go up higher, you make a high temperature, then you start to have vibrations as well. You add 2 more and you go to 7/2. So that's the idea of the Equipartition Theorem. It's really important, especially if you're talking about things like the specific heats that we'll talk about later. Rms speed, make sure you can calculate the root mean squared speed. So if I were to give you numbers, like 1, 2, 3, you can find the root mean squared value for those values, know how it relates to the average, and be able to calculate if I have a gas like, hydrogen gas at 20 degrees Celsius, what is its Rms speed? And then the Maxwell-Boltzmann distribution, it's most important to me. Now, the people in 251 got a whole other dose on this, but it's most important to me for you guys that you understand the Maxwell-Boltzmann distribution tells us that even at room temperature, we have some molecules, a very, very small percentage. Some molecules are going really, really fast. And now the Maxwell-Boltzmann distribution isn't going to apply exactly to fluids like it does to a gas, because it's not an ideal gas. But that means that in fluids as well, a room temperature fluid has some molecules that are moving really, really fast. So when those molecules get to the surface, they have enough kinetic energy to break the surface energy and escape. And so that's why evaporation happens in cool liquids, because the hottest molecules are allowed to escape so because they have enough energy in that molecule. But if you have evaporation, what happens to the average kinetic energy of the remaining molecules? It's always the highest kinetic energy ones that escape. What happens to the average? It decreases. And since temperature is proportional to the average kinetic energy, the temperature decreases with evaporation. If you have an enclosed environment, remember, molecules are going to come hit the surface and be absorbed back, raising the average kinetic energy. And so if you have an enclosed surface, you have a net amount, equal amounts of evaporation and I'll call it condensation. I'm pretty sure that's not right. But molecules coming back in, you don't have any net cooling then because you had going out coming in equally. Boiling, I did not talk carefully about boiling, so we won't have that on the exam. Humidity. Humidity, if it's just the word humidity, that's not what you think it is. Just the word humidity is how much moisture is in the air. Relative humidity is what you think of when you hear humidity. Relative humidity is the ratio of how much moisture is in the air to how much moisture the air can hold. The air can only hold so many water molecules before they start to condense. And so the relative humidity is telling you we have 75% of the amount of water in the air that the air can hold at this temperature. Hot air can hold much, much, much more water. It's not a linear function at all. And so at high temperature, if you have a high relative humidity, there's a huge amount of moisture in the air. At low temperature, high relative humidity may mean the air is actually really, really dry. It's just it couldn't hold much water and have little water in. And this leads to all kinds of cool things like in the morning you go out to your car and your window will have like a fog on a condensation. Why? Because your window is colder than the air. Molecules in the air are carrying moisture. It's below 100% relative humidity, so they can just hold it. Comes to the window that's cold, it gets colder, it can't hold as much water as it's carrying, and droplet forms. That's why you have fogging on your windshield. So, how do you get
Just to make sure, the distinction between humidity and relative humidity is how much water compared to how much water can hold.
Right.
Okay.
So how much water is the humidity? And then how much it can hold would be, the saturation point.
And it's a percentage, right?
It's a percentage, yeah. Relative humidity is a percentage. And if the more I've been studying weather stuff, the more I'm like, we should never talk about the humidity. We should simply talk about the dew point. The dew point is the temperature where with this amount of moisture in the air, you're going to be at 100% humidity. That's useful because as the temperature changes, the dew point still tells you how much moisture is in the air. And it tells you, is it likely to rain or not? If the temperature drops below that dew point, then you can't hold water in the air anymore. Now, of course, rain comes from up higher. But, it's an important consideration, something that would be far more useful. I actually went to a weather class a couple years ago. The teachers were really adamant, like, it's just stupid. These weather reports all talk about relative humidity. They should just tell us the dew point and go on. Okay, chapter 14, heat and heat transfer methods. We have three mechanisms for heat. Conduction, that's direct contact. Convection, an intermediary, like air or water, that transports the heat. And convection, that's electromagnetic waves, something we're going to learn about next semester. So you need to know those and know the equations that go with the power. So for conduction, the power for conduction is K times area times length times temperature difference. K is in this case, K we use all the time for constant. So that's the thermal conduction constant. So it's different for different materials. Convection, we have no equation for. Bet you this one's too thick too, yep. And for radiation, you have the Stefan Boltzmann law, and that's what this is. Epsilon is the emissivity. That's how efficient something is at radiating or absorbing radiation. 1 means it's a perfect absorber emitter. A perfectly black thing is a perfect absorber emitter and has emissivity of 1. Now, believe it or not, I know my skin doesn't look very black, but humans have emissivity that's around 0.97. So we're pretty good absorbers and emitters of radiation. An emissivity of 0 means it doesn't emit radiation, it reflects anything that comes to it. And with the thermos and talked about it, something that is silvered is essentially a 0 emissivity. White is a very low emissivity. This here is just a constant. It's the Stefan-Boltzmann constant. It does not change with material. It's just a constant. A is the surface area of the object. So for that homework problem, I said to treat a human as a cylinder. I don't remember how tall I made it and with a certain radius. So you can calculate the total area. Because if you want to calculate the surface area of your skin, that's kind of hard, right? So in physics, we make those assumptions. As you might have heard the joke about the terminal velocity of a chicken thrown out of an airplane. And the engineer is all kinds of technical, and the physicist says, well, assuming a spherical chicken. And that's the way we do things in physics. Okay, calorimetry. I already talked a bit about that with the problems, but remember, we have Q equals MC delta T if you're not changing phase. M is the mass of the object, C is the specific heat, and of course delta T is the change in temperature. So the heat is proportional to how much temperature change you have. If you're changing phase, then Q is equal to M times the latent heat. So you could have a problem that starts with ice at -5 degrees and ends with water at 20 degrees and asks you how much heat had to be put in. Well, you'd have to go from -5 to 0 using the specific heat of ice. And then at 0, you use Q equals mL using the latent heat of fusion, because fusion is the solid-liquid interface latent heat. And then you would have MC delta T going up to 20 using the specific heat of water. Ice and water, even though they're both H2O, they have different specific heats. Phase diagrams. Well, we use those a lot in our chapter 15 stuff, so I'm not going to talk about them here. The Joule equivalent of heat is just knowing that 1 calorie is equal to 4.186 joules. That number will be on the test, but knowing that calories, the historic unit for heat, is just a measurement of energy. And so you can instantly translate it. Now, let's say that I'm eating a 2,000 calorie a day diet. What does that mean? Go ahead, Leslie.
Isn't it like 1,000 of like those or whatever?
Right. 2,000 calories is 2,000 capital C calories. Nobody ever talks about that except for physics classes. A capital C calorie is a kilocalorie. In physics, we would write kcal, which is a great FM station in Southern California. And so if I'm eating a 2,000 kilocalorie diet, that means I'm eating 2 million of these calories, or 8.39 million joules in energy per day. You think about that way, that's a lot of energy. A candy bar has a whole lot of energy. You can do a whole lot of things with the energy in a candy bar. You just have to have a way to convert that chemical energy. And our bodies are good at converting that chemical energy. Chapter 15. I've gone through all the laws of thermodynamics, so I'm not going to go through the first law and the second law as it shows here. Thermodynamic work. You will be given the equations for thermodynamic work and change in entropy for each of these 4 types of transitions. So you don't have to have those memorized. Like I said, the calculus people may have to derive one of them, or they may have to something Maxwell Boltzmann. Your problem's going to be one of those 2 for the calculus people. But you need to know what isothermal means. So everybody with me. Isothermal means, what does iso mean? Constant thermal temperature. So isothermal, constant temperature. What does isochoric mean? Constant volume. What does isobaric mean? Constant pressure. And adiabatic? Well, not no change in energy. No heat. No heat. You could still have work, which means you could change the internal energy, but no heat. It's also called an isentrope because the entropy is zero if the heat is zero. So adiabats are also isentropic, constant entropy. Reversible and irreversible processes, I didn't talk about those, so don't worry about that. And like I said, I'm not going to go through the different statements of the second law here. Heat engine. Know the goal of a heat engine. What is the goal?
To convert thermal energy into mechanical.
Okay, convert thermal energy into mechanical energy. We're going to convert heat at a high temperature into work, and then we're always going to have exhaust of heat at a low temperature because the second law demands it. That means the efficiency can't be 1. You can't have all of the heat you put in converted to work. You're always going to have some waste heat. So you need to be able to calculate the efficiency is equal to the work out divided by the heat you put in. We call that Q sub H because it's the heat at high temperature. It's not divided by the net heat. That would be 1. Carnot efficiency. What's special about the Carnot engine? It's the ideal engine. It's going to give you the highest efficiency theoretically possible. And for the Carnot engine, which has its isothermal expansion, adiabatic expansion, of course I'm doing this the way I see it, isothermal contraction, adiabatic contraction, it has the relationship that heat is proportional to, well, let's use this, proportional to temperature. So if I write the efficiency using the fact that the change in internal energy for a cycle of a heat engine is 0, then work out is equal to Q hot minus Q cold. So this last form is equivalent to the first form. Work over QH is equal to 1 minus QC over QH. If I use that, since heat is proportional to temperature, then the Carnot efficiency is equal to 1 minus temperature cold over temperature hot. That's pretty easy to calculate if you know the temperatures of your hot and cold reservoirs. So you can make calculations like, well, we have ocean water that's at 50 degrees Fahrenheit, and we have sand that's at 90 degrees Fahrenheit. Can we make a heat engine between these? Yes, we can. What's the maximum efficiency we would get from that heat engine? This would calculate what the maximum conceivable value would be. What units do I have to use for my temperature here? Kelvins. Now, if you wanted, you could use Rankins. The Rankine is the equivalent to Kelvin, but based on the Fahrenheit scale. So you add, was it 459.6 or something like that to the Fahrenheit temperatures to convert it to Rankine. But we never talk about it. Nobody ever uses it. Don't waste your time. Then we have heat pumps. What's the difference in a heat pump and a heat engine?
The heat pump just moves temperature around, whereas the heat engine is trying to convert it into mechanical work. Okay,
if you change the word temperature to heat, it's right. The heat pump is moving heat. You put work in and it moves heat. So it's like a conveyor belt. Whereas a heat engine, you put heat in and you get out work. And so a heat engine and a heat pump are exactly reversed. Exactly reversed. So once you understand the heat engine, then for the heat pump, you're just taking all of the same things, but looking for a different outcome. Now, you're not converting work into heat. You're moving heat. You do have that work coming out, though, as heat, because you have still work is equal to QH minus QC. And so we talk about the coefficient of performance, not congestive obstructive pulmonary disease. There's no D there, so we're good. If it's for heating, then it's going to be the QH over the work you put in. If it's for cooling, then it's going to be the QC over the work. Because you're going to remove heat from one place, that's the Q cold. You're going to add heat to another place, that's the Q hot. And if you want to heat your house, you're going to use the coefficient of performance for heating. If you want to cool your house, you use coefficient of performance for cooling. A heat pump will do both, so you can use a heat pump in the winter to heat your house and in the summer to cool it. You just change which side is connected to the house and which side is connected to the outdoors. But you're going to have different coefficient of performance for heating as opposed to cooling, both because of the temperature differences and because it's the other heat you're looking at. Entropy, final topic. What is the statistical interpretation of entropy? What does entropy fundamentally mean?
Disorder.
That's the statement we commonly use, but that's not what it fundamentally means.
A probability that something is going to occur.
Okay? It is a number proportional to the probability of something occurring. Now that proportionality is not linearly, it's based on natural log to make our lives easier to work with some big numbers. But it's telling us about how probable something is. The actual calculation is based on how many different ways can I arrange this system and have the same pressure, volume, and temperature for the number of moles. So same PV, N, and T, how many ways can I arrange all of these molecules and have that same combination? And it turns out that at the one we're at right now, there's lots and lots of ways you can arrange them. Whereas there's only a limited number of ways we could arrange it to have all the molecules in a corner. Hence, the entropy of having all the molecules in a corner is very low. The entropy of where we are now is very high. Mike?
We have to know two versions of the equation, PV and KT and
PV equals nRT or PV equals N. You should be able to work with both of them. You'll be given both equations. You don't have to have it memorized.
Okay.
But you need to know a mole, lowercase n, is equal to number of molecules, capital N, divided by Avogadro's number. I mean, that equation is also given, but you have to have the concept in your head or it doesn't help you. Okay, for the rest of the review period, I was going to do problems, but I spent the first 15 minutes going over problems. So let's just do this one, and we'll be out of time. Much of the gas near the sun is atomic hydrogen. Its temperature would have to be 1.5 times 10 to the 7th Kelvin for the average velocity, Rms, to equal the escape velocity from the sun. What is that velocity? First, if this would be a little simplistic for a synthesis problem, but if it was a synthesis problem, you'd say, what's the concept? Even when it's not, that's the way to start physics. What's the physics problem? What's the concept? What's the idea here? 4 words. Big, hairy derivation I did in class. Kinetic theory of gases says that the average kinetic energy is proportional to the temperature. Average kinetic energy is, of course, 1/2 mass times average of the square velocity. And so that gives us the equation that VRMS is equal to the square root of 3 kT over m which I believe I only memorized it one way. But you can do it with molar mass or with the atomic mass, just changing because the difference in K and R is Avogadro's number. So all we have to do is put in And then I have to have the mass for a single atom of hydrogen. Well, what's the mass for a single atom of hydrogen? Anybody know? Yeah, me either. It's like 1.67 times 10 to the minus 27 kilograms, I think. Obviously, you have to be given that mass, but look it up. And then you just put that in your calculator. Question.
How did you know that it was this one specifically? The kinetic theory of gases. What gave it?
Because the kinetic theory of gases is what relates the speed to the temperature. All right, we are out of time. I'll see you tomorrow for the exam. I do have your redo exams all graded except for the extra credit for anybody who did an extra credit question on it. So I'll get those grades posted so you have a firm exam 3 grade, tonight.